Good morning, everyone. I'm pleased to present my research on the free vibration analysis of nanocomposite doubly curved shells reinforced with carbon nanotubes using a new integral high-order shear deformation theory. We start with general introduction. This research presents an analytical solution for the free vibration of doubly curved FG-CN3C shells, based on a novel integral high-order shear deformation theory. The model, using only for variables and hyperbolic warping function, accurately captures shear effects without the need for correction factors. Governing equations are derived via Hamilton principle and solved using Navi method. Validation and parametric analysis demonstrate the model's efficiency and its ability to predict the influence of material and geometric parameters on dynamic behavior. The objective of this research to understand the reinforcement mechanism introduced by the integration of CNTS within the shell's materials, of course, the doubly curved shells, and to evaluate the influence of CNT reinforcement on the dynamic performance, especially vibration behavior of doubly curved nanocomposite shells. In this section, we present the material properties of FG-CNTRC doubly curved shell to analyze the dynamic behavior of shell structures. Figure 1 shows the coordinate system of FG-CNT reinforced doubly curved shell and CNTS distribution pattern. To analyze the behavior of this structure, we use the volume fraction for each of the used disruption pattern expressed as, and the volume fraction of the elastic polymer matrix can be expressed as. In this section, we present the mathematical formulation used to analyze the dynamic behavior of doubly curved shell structures reinforced with carbon nanotube. The displacement field equation includes shear deformation effects without an additional twisting function. We then derive the result related to stress, focusing on the impacts of high-order shear deformation terms. Finally, we introduce the constitutive relation that defines the relationship between stress and strain using the flexible satisfiance. This formulation provides a strong theoretical foundation for predict the vibrational of composite nanostructure. This section presents different computational cases demonstrating the precision and accuracy of the given high-order shear deformation shell theory for predicting the free vibration characteristic of functionally graded carbon nanotube reinforced composite structure. Detailed comparative and parametrical analyses are included, incorporating results from other reported studies. Additionally, an FGCNT reinforced doubly curved shell is composed of a carbon nanotube disruption embedded within a polymer matrix, as illustrated in Table 1 and Table 2. Table 1 shows the mechanical properties of used CNTs and polymer matrix, and Table 2 shows CNTs efficiency parameters. Third table presents comparison of the first dimensional fundamental frequency of simply supported FG-CNT doubly curved shells with different shell theories and various geometrical configurations. The results shows the proposed theory predicts significantly higher and more accurate natural frequencies compared to classical models without requiring shear correction factors. The FGX distribution pattern consistently produced the highest frequencies attributed to the increased CNT concentration on the top and bottom surface, enhancing structural stiffness. The FGL pattern results in lower frequencies due to the concentration of CNTs around the mid thickness, which reduce reinforcement efficiently. The geometric configuration Rx 0.5 Ry 0.5 leads to the highest frequency, whereas the 0.5 minus 0.5 configuration yields the lowest values. The present results show excellent agreement with previous studies and demonstrate superior performance, particularly for the FGX distribution. This figure illustrates the variation of the first fundamental frequency of simply supported doubly curved FGCNT thick shells as a function of the curvature ratio, CNT volume fraction, and CNT disruption pattern. The result shows the FGX pattern achieves the highest frequencies due to CNT accumulation on outer surface, while FGL results in the lowest frequencies as CNTs concentration in the middle layer, increasing the CNT volume fraction from 0.11 to 0.17, enhance shell stiffness and rises frequencies. The minimum frequency occurs at Rx on Ry equal 1, where the curvature effect is limited. Thin shells are more sensitive to curvature variation, leading to a higher frequency, making thickness a key factor in structural design. In conclusion, the study introduced an enhanced high-order shear deformation theory tailored for CNT reinforced doubly curved composite shells, delivering both improved accuracy and computational efficiency. The results highlight the significant influence of CNT disruption pattern and volume fraction on the vibrational response, establishing a solid theoretical framework for the optimal design of advanced nanocomposite structures in engineering application.